Question: among electrical resistivity, thermal conductivity, specific heat, and Young's modulus and magnetic susceptibility, which quantities show a sharp change at the superconducting transition temperature? So we have to find which quantity shows the sharp change in the superconducting transition temperature. First, we will take the electrical resistivity. Okay, this is a graph between electrical resistivity as a function of temperature. At the transition temperature Tc, there is a sharp change in the resistivity. So therefore, this option is correct. If you see the given four options, so here electrical resistivity is not present. So this answer is incorrect. Your answer is either A, B or C. Now in this option also, the specific heat capacity is being present in all the options. Therefore, this has a sharp change at the superconducting transition temperature. This is a graph of specific heat as a function of temperature. It has a transition sharp change at the transition temperature. Now we will check for the thermal conductivity. So this is a graph for thermal conductivity as a function of temperature. If you see the transition temperature Tc, there is no sharp change in the transition temperature. So if the thermal conductivity is present in the option, that option is incorrect. So in option A, the option thermal conductivity is present. So this is incorrect. And in option C also it is there. So this option is also incorrect. So only the option B is correct. That is electrical resistivity, specific heat, and the magnetic susceptibility have a sharp change at the superconducting transition temperature. Question: a quarter wave plate introduces a path difference of lambda by 4 between the two components of polarization parallel and perpendicular to the optic axis. An electromagnetic wave with electric field E is equal to x cap plus y cap into E naught e power I k z minus omega t is incident normally on the quarter wave plate, which has its optic axis making an angle of 135 degree with the x-axis as shown in the figure. The emergent electromagnetic wave would be option A elliptically polarized, option B circularly polarized, option C linearly polarized with polarization as that of the incident wave. Option D linearly polarized but with polarization at 90 degree to that of the incident wave. So in this question we have to find what is the conditions of the emergent electromagnetic wave from the quarter wave plate. So first we will write the given electromagnetic wave, that is E vector is equal to x cap plus y cap E naught e power I k z minus omega t. So this exponential term can be written in terms of sine theta and cos theta, that is cos k z minus omega t plus I sine k z minus omega t. Now multiply the E naught and x cap plus y cap inside the cos theta and sin theta term. You will be getting E naught e power I k z minus omega t x cap plus E naught e power I k z minus omega t y cap. Now we have the x component and the y component of the electric field. We will write what is the magnitudes of x component and y component. That is E of x is equal to E naught e power I k z minus omega t, and the y component magnitude is E naught e power I k z minus omega t. Now if you see the x component and y component, the amplitudes of x and y components are same. So if amplitudes are same, they are called as a linearly polarized with polarization as that of the incident wave. So answer is option C. Question: a p-doped semiconductor slab carries a current I is equal to 100 milliampere in a magnetic field B is equal to 0.2 Tesla as shown. One measures Vy is equal to 0.25 millivolt and V of x is equal to 2 millivolt. The mobility of the holes in the semiconductor is dash. So in this question they have asked us to find what is the mobility of the holes in the semiconductor. So this question is based upon the Hall effect. So here the magnetic field is along the z axis and the current is along the x axis. So the Hall voltage is along the y direction. They have asked us to find what is the mobility of the holes, that is mu p is equal to sigma of p into RH, where sigma p is the conductivity of the holes and RH is the Hall coefficient. So we have to find what is the value of conductivity and the Hall coefficient to find the mobility of the holes. So first we will find the Hall coefficient. RH is equal to E vector due to the Hall effect divided by current density into magnetic field. So Ey divided by current density into magnetic field. The electric field in terms of voltage is given by V divided by width of the slab, and current density can be written as current divided by area. So for area we can write thickness into width of the slab. So by simplifying this we will be getting V voltage thickness divided by current into magnetic field. Now we have found Hall coefficient. We have to find the conductivity of the holes. Sigma is equal to L divided by resistance into area. That is L divided by voltage divided by current into area is thickness into width. So by simplifying it, we will be getting current length of the slab divided by voltage into thickness of the slab into width of the slab. So now we have to substitute RH and the conductivity in the mobility of the holes formula. So by substituting it and simplifying it, we will be getting voltage into length of the slab divided by magnetic field width into voltage along the x direction. Here which direction is very important. So based upon that we have to take the value from the given question. So by substituting all the values, we will be getting the mobility of the holes as 1.55 meter square per volt second. Question. Inside a large nucleus, a nucleon with mass 939 meg electron volt per c square has a Fermi momentum of 1.4 Fm inverse at absolute zero temperature. Its velocity is x into c, where the value of x is dash. So in the question, they have taken a large nucleus and they have provided us the mass of the nucleon and also the Fermi momentum value. They have said velocity is equal to x into c. They have asked us to find what is the value of this x. We know that Fermi velocity V of Vf is equal to h cross kf divided by m. Now multiply and divide by c square on numerator and denominator. So we will be getting h cross c kfc divided by mc square. In the question itself they have given h cross c value as 197 and here the Fermi momentum value is given as 1.4. So here 1.4 is written and C can be kept as it is. And the mass value is given as 939 meg electron volt divided by C square. Here also we have one more C square. So both will cancel off and we will be getting 939 meg electron volt. So by simplifying this, we will be getting the Fermi velocity as 0.29 into C. So here they have already given in the question Vf is equal to x into C. So by equating these two, we will be getting x value is 0.29. Question. An electromagnetic plane wave is propagating with an intensity I is equal to 1 into 10 raised to 5 watt per meter square in a medium with epsilon is equal to 3 epsilon naught with mu is equal to mu naught. The amplitude of electric field inside the medium is dash into 10 raised to 3 voltage per meter. So in this question they have given the intensity of an electromagnetic wave and they have asked us to find what is the amplitude of the electric field. So intensity is given by the formula I is equal to 1 by 2 root of epsilon divided by mu into E square. We have to find what is the value of E, that tells you the amplitude of the electric field. So in the question they have given epsilon is equal to 3 times of epsilon naught and mu is equal to mu naught. So by substituting it, then we will be getting E square is equal to 2I root of mu naught by epsilon naught. So all the values are given in the question. By substituting it, we will be getting E is equal to 6.6 into 10 raised to 3 volt per meter. Question. Two solid spheres A and B have same emissivity. The radius of A is 4 times the radius of B and temperature of A is twice the temperature of B. The ratio of the rate of heat radiated from A to that of from B is. So in the question, they have taken a two spheres A and B, and they have asked us to find what is the ratio of rate of heat radiator, that is QA divided by QB. So we know that according to Stephens-Boltzmann law, the rate of heat radiation Q is equal to A into sigma epsilon into T power 4. So here A is the area of the emitting body, and sigma is a Stephen-Boltzmann constant, and epsilon is emissivity of the body, and T is the surface temperature. They have given epsilon, that is emissivity of A is equal to emissivity of B, and the temperature of A is twice the temperature of B, and radius of A is 4 times the radius of B. So QA divided by QB is, as it is a sphere, we can write the area is 4 pi r square, that is 4 pi radius of A square into emissivity of A sigma T power 4, and divided by the heat radiation from the object B. So here RA can be written in terms of RB, that is 4 times of RB, and in the question they have given emissivity of A and B are same. So we can write emissivity of B here, and temperature of A is twice the temperature of B. So 2 times of TB the whole power 4. So by cancelling the common terms, we will be getting 16 into 16, that is 256. So the ratio of QA divided by QB is equal to 256. In the description box, you can find the link for GATE Physics 2019 and 2020 solution. Please share and subscribe the channel. If you have any queries, write in the comment section.